thank you. So in photodiode, we have discussed that how this will work and this thing. So it is simple PN junction diode, and it will convert optical energy into electrical energy or light energy into electrical energy, whatever you can write, it's not a problem. Okay, electrical energy, that is electrical energy under reverse bias condition, so using photovoltaic effect. Okay, by using photovoltaic effect. Okay, what is the photoelectric effect? We have studied in first unit what is the photoelectric effect. Did you remember photoelectric effect?
Emission of electrons.
Yeah, emission of electrons.
Where
How
light.
they are?
When the light is passed through.
Yes, that's good. That's great. Okay, photoelectric effect. Okay. Now the difference is here. Suppose you have a metal here. Suppose any metal or material, semiconductor, whatever. Okay. If you take metal, if you incident some light here. Okay. If you incident some light here, electrons come out of this surface. Electrons will emit, and these electrons come out of the surface. So these electrons come completely from the material. Okay, the electron leaves the material. But in photovoltaic effect, same thing. This is also same phenomena, but here electrons will stay within the material only, within the material. So here also you are shining light or incidenting some light. Here also electrons are generating, but these electrons are not leave the material. Okay, these electrons not leaves material or semiconductor, whatever you can say. Okay, so this is the photovoltaic difference between photoelectric and photovoltaic. In photo, please mute. It's A4, please mute, ma'am. So in photoelectric effect, when you shine the light on metals, electrons come out of the material. But in photovoltaic effect, what happens? When you shine the light, electrons will not come out of the surface. Electron will not leave the material. They will stay within the material only, but they are free. That is the difference between these two. Okay. In photodiode or sensors and photodetectors and solar cells, we use only photovoltaic effect. Photovoltaic effect. So we are using light and free the electrons. We are generating the electrons. We are creating the electrons, but these electrons are stay within the material. This will not come out of the surface. This will not leave the material. They will stay within the material only. Okay, that is the difference between photoelectric and photovoltaic. Okay, so if you take solar cell or photodiode, photodetector or photodiode, principle is same. First, we have to generate electron holes, generation of electron and holes. Okay, first point. Second one is separation of these electron holes. Separation of electron and holes. By how you are separating? What you are using to separate these electron holes? What parameter you are using in the solar cells or whatever? Okay, what you are utilizing here, please tell me. Huh? How you are separating generated electron holes? Okay, please tell me. You are generating electron. Huh? Somebody saying I cannot hear you.
Yeah, light energy.
Light energy. No. We are generating electron and holes by light energy. But after generating electron holes, we are separating these electron holes. How we are separating these electron holes? What we are utilizing? Every day we are discussing PN junction diode. Second unit onwards we are discussing this point. Don't know? Every day we are discussing on this one. Still you, I don't know what to say. Internal electric field. Have you forgot this one? using internal electric field, whatever generated electron holes, immediately we are separating. Okay, this is the internal electric field. When PN junction started, that day onwards we are discussing this about internal electric field and the job of internal electric field. And third one is collection of these charge carriers. Okay, collection of electron holes, or you can say by how we'll connect by using some metal contacts. Okay, this is general principle of any photo detector or solar cell working function. You write these 3 points. These are very important. Okay, working principle of the solar cell or photodiode. These are 3 important points. Without writing this one, there is no meaning of writing anything. Okay, first you write the first point is to write PN junction is a simple photodiode is a simple PN junction diode. It converts optical energy and electrical energy by using photovoltaic effect. Okay. So the main principle of this photodiode is generation of electron hole pairs by some light, incident light, then light. And after that, generation of electron holes will be separated by internal electric field, and these separated electron holes will be collected by some metal contacts. Okay, this is simple working of photodiode. Okay, so yesterday also we have discussed this thing. So just I will quickly go through this one, and because we have to discuss many things. So when you combine this one, PN junction diode, okay, here you have to, this is the interface at the middle, okay, left side, you have a depletion region, and right side also you have a depletion region. And here we are connecting this one is a reverse bias condition, okay, under reverse bias conditions, okay. So left side is P type semiconductor, right side is N type semiconductor. Here holes are the majority, here electrons are the majority, right? So when depletion region is forming, that means P side it is leaving a negative charge density, and right side, that is towards N side, positive charge density. Because of this one, we are having a internal electric field. Okay, internal electric field. Here potential, you can write battery minus and plus signs. Okay, this is under reverse bias condition. Now we are shining some light here. Okay, we are shining some light throughout the semiconductor. Okay, please listen carefully. Throughout the semiconductor, we are shining the light. Okay, so in the bulk region, this is bulk region. Here also electron holes are generating. In the P bulk region also electron holes are also generating. In the depletion region also electron holes are generating, right? 3 regions we are generating electron hole pairs. But here whatever generated electron hole pairs in the depletion region, the electric field direction is +2 minus. So this electric field will send these holes towards the P side, and these electrons it will send towards the N side. Okay. So it will first we are generating using some light electron holes. This electric field, internal electric field, we are utilizing this electric field and sending holes towards P side and electron towards the N side. So in the bulk region also electron holes are creating, but here these electrons and holes are recombining. Before separating, this will recombine, or instead of that one here, okay. Okay, instead of this one, there is no electric field in the bulk region. So here these electron holes are recombining, or generated electron holes immediately recombine, because there is no field to separate. There is no field to separate. Similarly, if you take P type region, in P type also, these electron holes are generated by light, but there is no electric field here. Here immediately this electron hole will recombine. That means even we are generating by using light, but these are recombining immediately. These are not producing any current. These are not producing any current because there is no field. That's why these are recombining. So whatever generated electron holes in the depletion region are separating by internal electric field. Whatever generated electron holes in the depletion region are useful for current in a device. Useful for current in a device. Okay. So that is why our active area in a detector is this is depletion region only, our active area for a device. Okay, active area. So that's why whatever generated here, that will be useful for current. Okay, these are creating a current in a circuit. Okay, so this is the simple working of. So after this one, after separation, we are collecting metal contacts, these electrons and holes. Okay, now if you see this one, okay, now we'll see construction of these photodiodes. Okay, is this clear to you everyone? How the electron holes are generating, how we are separating, how we are collecting? Is it clear to you everyone?
Yes, sir.
Okay, next step we'll go to the construction of photodiode. Similarly, as we have constructed PN junction, here also same thing. Here we will take N type substrate or N plus layer. Okay, N layer or you can take any layer. Okay, here we will deposit on a P layer. PN junction is created. Okay, after that here we will create a some metal contacts front side to collect the charge carriers, and the bottom also will connect a some metal contacts. That metal may be aluminum, copper, silver, platinum, gold, whatever you can take. Okay, depends on our requirement, we will take the aluminum. Okay, this is metal contacts. Okay, and top also these are metal contacts. Okay, so we are shining light here. Okay, we are shining light here. Here electron holes are creating, only holes moving upside towards p side, electron moving towards n side. So there is no recombination losses, because only, if you see previous diagram also, if you see previous diagram here, only in P region only holes are coming. In N region only electrons are coming. So electron and electron, the electron density is increasing in N side. Similarly, only hole is coming in P side. So hole density is increasing. So there is no recombination losses under reverse bias condition. There is still some losses are there, but negligibly small. Okay. Here see one more point here I want to tell you. Here reverse bias applied. So in the p type, holes are the majority. This will also sometime diffuse. Some of the carriers will diffuse. And in n type also electrons are the majority. This will also diffuse. So here at a time, even you connected in reverse bias, there is a diffusion process takes place and drift process also takes place. But in case of reverse bias, the drift is dominant. In reverse bias, drift is dominant. So diffusion is very small. Okay, that is, we'll see when we discuss IV characteristic. We will discuss. Okay, that point. So now here the construction is same. First we will take N type substrate or N type layer. After that we will deposit P type layer. After that front and back we will use code the metal contacts. Okay. Using this one, once electron holes will be generated, only holes will move towards P side, only electron move towards N side. These will be collected by metal contacts. This is simple working of the simple construction of the photodiode. Okay, if you see circuit diagram here, so here this is the, so for LED we have put the outside arrows, so here inside arrows, because the symbol simple PN junction diode symbol is this one. Okay, this is simple PN junction diode, and second one is we are drawing LED symbol. This is LED symbol, this is LED, and this is PN junction, and third one we are drawing is solar cell symbol. This is light is sorry, so light I will draw a little bit. So here you can draw the solar cell solar symbol or photo detector. Okay, light is receiving here, so inside arrow mark. Okay, for LED outside arrow mark. Okay, that is the symbol. Okay, here you can connect the resistor. Okay, again this is series resistor, and after that you are giving reverse bias condition, and in the middle you can connect ammeter to measure the current. Okay, to measure the current. This is the simple circuit diagram of solar cell. This is plus and minus, sorry, photodiode. So whatever generated electron holes will be separated and this will go to the ammeter. Here we will measure the current. How much current flow is in the circuit. Okay, how much current is flowing in a circuit we can check out using the ammeter. Okay, here series resistance is connected here resistor. Why? Because sometime we will apply high reverse bias voltage. That time there is a chance of damaging of this device. Okay, or that's why to protect this device or protecting this photodiode, we are connecting some resistor. This will stop the overflow current. Okay, high current. This will stop some of the. Okay, that's why we are connecting this series resistor. Okay, so after that we will draw the IV characteristics. Okay, we will draw the IV characteristics. First, you take the. This is very important. So without IV characteristics, you cannot justify the device. You cannot say it is working properly or not. Okay, first you take voltage on y-axis and current on x-axis. Current on x-axis. See, same thing. So this is forward. So we are applying some voltage as like a simple forward bias. If you take, it's like a this one. Or if you take a, if you swipe a voltage, this will be look like a this current. Okay. Or I will take a different color. Then it is convenient for you. Okay. Okay. Just I will take a different color for a dark current. Then okay. Let's take a dark. So first we are measuring under dark conditions. Okay, dark means we are not shining any light. Okay, this is dark characteristics. Okay, dark current means we are not shining any light on the device. So because of this reverse bias, we are having some current. Okay, that is what dark current means. So after that, we are illuminating some light. Then there is a some current will flow in a device. Some current will flow in a device, that is photo current. Now we'll see that is. So once you shine the current light, there is a generation of electron holes. So current will increase in a device. So the curve will shift downside. Curve will shift down. Sorry, this. The curve will shift downside because of higher. So just like just this way. Okay, this is photo current. Okay, you got it right. So first dark means without any. Suppose here you have a device here. Okay, here you have a device. You don't. First you are not shining any light. That is dark current. Whatever you will get dark. So here you can see in the diagram also. First one, here you are not shining any light here. Some current will get because of this negative bias. Okay, negative biasing voltage. You are getting some current. After that, you will shine your light. Okay, some light will shine on the device. Once you shine the light, there is a generation of electron holes. These generated electrons holes, what we are saying, photo carriers. What is that? Photo carriers. Because photo means light, carriers means electron or volts. These are generating by some light. That's why we are calling photo carriers. Okay. Once you shine the light, current will increase. Why? Because electrons and holes are increasing in a device. Okay. That's why the curve is here, current is almost zero. In dark case almost zero. But in photo case there is a some current in the negative axis. Okay. So this one, this point we are calling a short circuit current. Okay, short circuit current. This point on the voltage axis we are calling a open circuit voltage. Open circuit voltage. Okay. Now see what is short circuit current and what is open circuit voltage. Okay. So is it clear to you what is the dark current and what is the photo current? Is
Yes,
it
sir.
clear? So dark current means we will not shine any light on the device. We will not incident any light on the photodiode. Only in reverse bias we will measure the current. That is dark current. So photo current means when you light incident on the device or when you light incident on the photodiode, because of this light, electron source will be generated. These are extra electrons and holes. Because of this extra electron and holes, extra these electron holes will be flow in a circuit. That means we are getting extra current. This current we are calling a photo current. That's why compared to dark and photo curve, the curve is shifted downside. So negative axis, along the negative axis, the current is increased. Here along the negative axis, if you neglect the sign, the current is increased when photo is illuminated on the device. Okay, that is the I short circuit current. Now we'll see short circuit current and open circuit voltage, or you can, I am writing for complete short circuit current, and VOC means circuit open circuit voltage. These are very important. Okay, so here thing is short circuit means, so here ISC, you see the point at ISC. Here what is the voltage here? What is the voltage at this point? Please see the curve and tell me what is the voltage at ISC point. At the point of ISC, what is the voltage? What is the voltage value at ISC point? Here, can you see? See, otherwise you can tell me what is short circuit current. Please see the terms there and tell me what is short circuit current. Anybody try to see that words and tell me. Anyone? At least tell me what is the voltage at ISC point. Are you there or not?
Yes.
What is the value of voltage at this point at ISC? Suppose I am marking arrow. At arrow, what is the voltage value? Or you can say, suppose you take x-axis, we are taking voltage. So what is the current on y-axis? X-axis, sorry.
Zero.
What is the current here? What is the current
Zero.
here? Yeah, zero. Same thing. Now you got it right. So same thing at the current axis, that is y-axis, voltage is zero. So here voltage is zero for short circuit current. So what is mean by short circuit current? Please see the terms here. Short circuit current. So here very simple. Just when your device is shorted, maximum current flows. When device shorted, maximum current flows through a circuit, or maximum current flows through a device. That is called ISC. Okay, no need to worry for these terms. Just you understand that word, short circuit current. So when your device is shorted, maximum, that means shorted means we are connecting two terminals directly. Okay, we are not connecting separately. So we are, whatever we are connected to this potential here, one terminal is connected negative potential, one terminal is connected to positive potential of the battery. We are removing battery, just we are connecting. We are connecting just two terminals, we are connecting. That is short circuiting. Our device is short circuiting. When our device is short circuited, maximum current flows through a device. That maximum current we are calling short circuit current. That is what here, this is the maximum current we will get in a device. Okay, this much, suppose this is value will change, depends on parameter, but this is the ISC is the maximum current in a device. Okay, maximum current in a device. Next one, open circuit voltage. What is open circuit voltage? So when device is open, here also when in short circuit current voltage is zero. Similarly, when open circuit voltage, current is zero. Current is zero, right? So here open circuit voltage means when device is open, maximum voltage drops across the device. Maximum voltage drops across the device. That is the when device is open, or open means we are not switching on, opened. Open connection and a closed connection, right? You know, right? Switch is there. Suppose open means there is no connection. Open means no connection. On means it's connected. Okay. Open, when device is open, maximum voltage drops across the device. This is we are calling open circuit voltage. Open circuit voltage is nothing but just when your device is open, we are not connected. That if we are not connected means current is zero, right? So if you take a small example in our home, if you switch on the switch, if you put on the switch, then only bulb will glow. That means current is flowing. When you switch off, there is no current force, so bulb will not glow. That is same thing here also. Current zero means circuit is opened, device is open. So when device is open, voltage drops only we will observe. That is what VOC means. That is what maximum voltage drop. Okay. So now we got ISC and VOC. Now always here. So always photodetectors will run on a short circuit condition mode. So photodiode or photodetectors, whatever you can say, this will run on short circuit condition only. Short circuit conditions. Short circuit condition, and the solar cells, whatever we will discuss this one. Solar cell will work on open circuit condition. Open circuit voltage. Open circuit voltage condition. Okay, so photodiode always will work on short circuit condition and solar cell will work on open circuit condition. Okay, now we will see. So why we are operating in short circuit condition, we will see now. So suppose as we have discussed here just before, this is dark current. Okay, this is dark. I am drawing again dark. And when you shine light, there is a current here. Okay, there is a current here. This is the light current. Okay, photo current, or you can say photo current, whatever you can say. So if you increase the light intensity, we are shining the light, some light. If you increase this intensity, the VOC will not change. Only the ISC will change. If you increasing the intensity, what will happen? Current will increase or decrease. So we are shining the light on the device. If you increase the intensity of light, what happens? Electron holes will be, more electron holes will be created, right? You got it?
Yes.
Point. Here you have a device here. So here some light, suppose 10 photons are incidented on this one, 10 photons. So that time here 10 electrons and 10 holes are created. Suppose here you are increasing intensity, that means 20 photons incidenting. That means 20 electrons created, 20 holes will be created. So light intensity, if you increase light intensity or illumination intensity, so current also increase because of increase in charge carriers, increase in photo generated charge carriers like this. But here VOC is not changing. VOC is not changing. ISC 1, ISC 2, ISC 3. Okay. So ISC 3 is greater than ISC 2. Okay, ISC 2 and ISC 1, because the current is increasing if you increase in the illumination. This is the actually characteristics of a photodiode. Okay, you have to draw this way. Okay, first what you have to do, this is the dark characteristics. Okay, just you draw dark just like this one. Okay, sorry, just I'll draw a little bigger, then it will be clear. Okay, so first you draw the current and voltage axis. This is current and this is voltage. First you draw the dark characteristics. This is dark. Okay, when you illuminate some light, there is a current curve will shift down. Okay, this is the photo current. Next one is photo current. So if you increasing the intensity of light, okay, light intensity, the current will also increase in a device. Okay, like this will increase. Okay, the curve will shift like this. Okay, this is the ISC. Okay, so current also increases. Short circuit, if you increase the light intensity, ISC also increases. ISC also increases. That is what you have to. If they ask IV characteristics of a photodiode, you have to draw this diagram. Okay, this is the characteristics. Okay, now we will see equation, that is here total we have two currents. One is I diffusion current and I drift current. So the drift current and diffusion current always opposite direction, right? Always opposite direction. So you will take a minus sign there. Exponential I Q VR by KT minus 1. Okay. Here minus Q P0 Q H nu P0 by H nu P0 by just a second, I will write this one. Sorry, just a second. One more two things are there, I will explain that also. This is neta PZ neta P0 by P0, or you can write just okay, no problem. Q0 Q by H nu. Okay, this is the first term is due to drift and second term, first term is due to diffusion current, second term is due to drift current. Here P0 is the incident power, incident light power, incident photons power, or you can write, okay, light power of the incident light. Okay, eta is the quantum efficiency, Okay, these two terms we will discuss. Okay, the IV characteristics is photodiode is diffusion current plus drift current. Why we are taking here minus in the middle of the two terms means drift current is always opposite to the diffusion current. That's why we are taking here minus curve. Okay, this is H nu, you know, H is Planck constant, nu is the frequency, and this is Q is the charge of electrons. Okay, this is the, but here drift current is very less. That's why we are getting negative current, right? If you see this characteristics, so I, if you take I, this is negative axis, right? Isn't it? This is top side is positive and bottom side is negative. So current, why we are getting negative means drift current is dominating in this process. That's why. So second term is higher compared to first term. That's why total current we are getting negative values. You got it right? Why we are drawing in the third and fourth quadrant? Why we are drawing IV curve in third and fourth means the second term will dominate. Okay, second term, that is drift current, will dominate in photodiodes. Okay, so this is the equation, and here two terms are how you will characteristics means characteristics of a photodiode. Okay, first one is responsivity, that we will discuss tomorrow, responsivity, and second one is quantum efficiency. These two are very important, and third one already we have discussed, this is IV characteristics. Okay, IV curve. So any device you want to test characteristics, how these are working properly or not, first one IV characteristics, second one responsivity, and third one is quantum efficiency. Responsivity, quantum efficiency